This conference will now be recorded.
Okay, good morning, everybody. Welcome to the OCP HPC project regular meeting on June the 13th already. The year is going by fast. Who just joined? Hi, Philip. How are you doing?
Okay, you?
Good. Now, so just need Andrew Philip. Okay. So I've got a couple of minor updates today, which we'll go through, and we can maybe open up the discussion a bit more on next steps. And sorry, I think somebody else just joined on. Victor. Hi, Victor. Welcome again. Okay, so as usual, we'll start with introductions. So Ara Strogan, would you like to just give an introduction to everybody, please, if you don't mind again?
Yeah, hi everyone. I'm Aras Doğan. I'm a CFD engineer, and I generally work on aerospace field. I also work with Ender Demirel on thermal structures of some designs. So yeah, that's actually why I'm here. We are interested in the thermal modeling of the HPCM module.
Great, thank you. Welcome aboard, Aras. Sorry, yeah. What was the name of the company?
It was MSBAI, MSBAI.
MSPAI.
MSBAI.
B for Barry. Okay.
Yeah.
And you said it's a US-based company.
Well, you know, I work at MSBAI, but I also work with Ender Demirel. Those are two separate works for me.
Right. Okay. Okay. Thanks. And just somebody else just joined, Andrea. Hi, Andrea.
Hi, hello.
Andrea, is this your first time, Andrea?
Correct.
Okay, if you wouldn't, oh, hang on a minute. Would you mind giving a brief introduction?
Yeah. So hello everybody, I'm Andrea Moschini. I'm working from Vertiv as product manager for cooling units in Vertiv since 6 years.
Sorry, what was the name of the company again? I missed that.
Vertiv.
Veritiv, V-E-R-I-T-I-V-E?
Correct.
Thank you. Welcome aboard. Okay, I'll update that later. All right, so I think that's it. Is there anybody else new that hasn't introduced themselves before? Okay. All right, everybody. So the first topic really is we on the last meeting I guess we went over the thermal architecture a little bit more, and we had a good discussion. That one was really useful, so thank you for the inputs. I did have a number of offline discussions as well, which I can touch on, and maybe Ender, you can maybe add a bit of color to my overview as well. But a couple of things that popped in. In fact, what I should do is I should open the model, which might take a little bit of time to open, but let me just do that now. Except for I go away from to download. That's the one I want to open. As there's a number of new people on here that may have missed or haven't seen the recording. So I'll load that once that's loaded. So basically, I built the full wall, or my cartoon of the full wall, so to speak, in the 3D model. And we were talking about the cooling. So we were talking about an internal cooling loop of 16 vertical modules, and we had a pump that they would pump around. It was a two-phase system, so the pump would pump around one vertical column, and then we had to have a heat exchanger which I referred to Alpha Laval was I think the heat exchanger that I met them at the OCP Prague, and Alpha Laval had a fantastic small, really tiny heat exchanger. It was 15 kilowatts. So they said they could add more plates and up it to about 20 or 30 kilowatts quite easily. And that would be more than adequate for the column cooling. So so we had that. So we had a cooling loop on each of the columns. But one of the discussions with Greg from IABRA mentioned thermosiphoning, and the possibility that we might be able to leverage that rather than actually pump the water around that loop. Now, I think there's a lot of work that needs to be done there in further discussions with both him and Ender and Chate and the RISE Institute, which is Research Institute for Sweden.
Yeah, if you want to include Boyd in there, happy to do it. We do build thermosiphons.
Oh, excellent! So it'd be interesting to see if it's even viable. I mean, it was one of those. I don't think any of us really knew. It was just okay. It was quite an interesting. So actually, on that, Philip, what I'll do is when this model finally loads, I will actually just quickly go through it again, and we can just see if there's any viability there at all. You know, I think it was just really ideas we're having. In fact, there you go, it's open. So on that note, why don't I just show what's going on here? So this is a little bit of a review from our last meeting as well. So this is the actual physical wall that we would build. And you can see one of our modules is plugged in at the bottom. So this is just showing how the wall would be structured in the data center. So you can see that basically we've got a column each. So we have a single cycle loop going on here, and this was the Alpha Laval heat exchanger. This is this isn't to scale. I think theirs is actually smaller, the one they showed me, which could do 15 kilowatts, and they could add a few more plates to get up to 30. Because I was amazed at how small it was. And I just put a pump. Again, this is just a cartoon pump. This is not necessarily realistic to circulate the water. We were talking about potentially having the negative pressure in both directions, so if you did get a leak, it would suck the water back into some reservoir, I guess. And the key thing of this, when I was explaining it, is we want the return hot water to be 65 degrees C for energy recovery. And so we were talking about having a couple of valves, variable valves on the inlets, so that you could, and measuring the temperature on the outlets, so that you could actually, depending on the power of each module, you would be able to cool it appropriately to get the 65 degrees C water out of it. Obviously, if you didn't control it by every module and the modules were burning different amounts of power, you'd end up with one module having very hot water coming from it, and other modules giving cooler water if you only had one valve at the top. So that was why it was a valve at a time. So the idea that came forward was potentially with thermosiphoning, we wouldn't need the pump. But I did also explain the way the water actually zigzags through the top and the bottom, these water chambers in the module. And so there's a lot of complex flow going on there, and I'm not sure whether that would be sympathetic to any siphoning approach, or where you are, or where your module is in the column. So again, it was just one of those sort of passing comments from somebody that said that might be an interesting investigation. So Philip, I don't know if that if you know the detail of that to say no, that's never going to work, or whether it is worth investigating to a greater or lesser extent.
It'd be good to take a look at it. Negative pressure though, with that's a 2 meter tall column of water.
Yeah, just about. Yeah.
Yeah, it's going to be tough to locate the vacuum pump in the right place to make sure that you can suck. Like the vacuum pump would need to be at the bottom for it to be effective, right?
Actually, so that's a good point. Just on this, I've sort of shown the wall with the first module being at the very bottom of the wall. I mean, this could be a false floor, and we could have the water going underneath. There could be different arrangements for sure. Okay, so that was just one sort of passing comment, and then so Chate and Ender, who's on the call. For those of you that remember, they actually presented at last year's OCP Global Summit in the Future Technologies Symposium on some thermal modeling that they did for us on the actual main chip in the module. And they actually won the award for the best paper in the HPC track. So Chate then moved across to the RISE lab, the Research Institute of Sweden, and he worked with a chap called John Summers, which is, I guess John's been fairly heavily involved in the thermal side of managing data centers over there, and in the wider compute area. And anyway, so we had a meeting just after our last meeting, and with Ender, and Ender's from. So you're still with DM Tech, or did you say the name's changed, Ender?
DS Tech.
DS Tech. I got you as DC. Yeah. Right. I'll change that. Yeah. So Ender's with DS Tech in Turkey, which is a university, right?
No, it's a small company. SME.
Oh, beg your pardon. And so he actually did the simulation. He runs the open foam, the open source CFD tool. And long story short, from our discussion just last week, that RISE has a fairly big computing cluster that they've given Ender access to, so that he can do some more thermal simulations. On that note as well, if you weren't at the last meeting I did up, you'll notice that we don't have the tall walls on the water cooling here anymore. We actually have I've lowered these walls, and I've changed the cooling structure. This is a simplified model, so you can't really see it here. But basically, we're trying to pick up a conduction cooling of the module itself down to the water running through the veins of this heat sink. And so one of the first things, hopefully we can get a sort of a piecewise thermal model of the whole lot. But one of the ones I'm mainly concerned about is whether my ideas on cooling these 25 watt to 40 watt modules conductively into a water channel down here is actually going to work or not. Specifically, the way the module gets friction connected to the water from a thermal conductor. So the thermal resistance of that joint is my biggest concern. So we're doing so Ender's going to start with some simulations on that. Ender, any further update from yourself in terms of what I said there? If I missed anything?
Alan, as you pointed out, RISE will allocate some computational resources consisting of about 2,000 nodes for the simulations. So we are using open source tools for the thermal simulation of IT systems. So we are planning to use OpenFOAM for the heat transfer analysis. And I want to give a brief information about the thermal model. The heat conductivity is a very critical point for this design. So there are two fluids in here, water and air. In order to accurately model heat transfer between air, water, and solid, we are planning to use a conjugate heat transfer numerical model for the realistic simulation. So we received the three-dimensional CAD files, and we are focusing on the computational modeling of this design. There will be two designs. The first one is for the HPCM, for a single HPCM. The second one is the wall, the single column of the wall, in order to model the pressure difference or negative pressure in order to reduce power consumptions by the pumps. So we will be sharing our results maybe next meetings. Alan, that's all.
Okay, great. Well, thanks, Ender, for that update. What was I going to say?
Alan,
Yes, yeah, Michael.
can you just touch up water flow on this first column? There's a this brown the column bar, and then
Yeah.
it has a pair, right, left and right, based
Yeah,
on.
so basically this is the heat exchanger here. So you'll have the facility water will flow through the heat exchangers. So once you've exchanged the heat, the cold water will come down this column here. And it will in the non-thermo siphoning one, it will be pumped down, or the pump would be somewhere in the loop. And you would have these valves on each going into each of the modules. These valves here, again, this is just a cartoon, so we need to turn this into something real. Would control the flow of the water, of the cold water, into the module, such that, if I can get this to work, that's it. Such that the outflow of the hot water on the hot side would be 65 C centigrade outside of the coming out of the module, and then all the hot water returns from all of the modules would rise up and go back into the heat exchanger at the top. Is that what you wanted, Michael? Does that clarify?
Okay, good. Yeah. Thank you.
And so these are all independent, separate phases for each column going into the single infrastructure water system.
Okay, got it. Thank you.
So one thing actually, so on this, one thing that John Summers did bring up at RISE in our discussion was if you're returning 65 degrees C hot water, eventually, no matter how much insulation you have, the actual room itself will raise to 65 C if you don't do any level of cooling of the room. So that was one thing that I've not really emphasized here, but that is one thing we need to think about. Is I was of the mind that we would try to insulate these modules and the main processor. So this actual, where the water was, didn't need to be, these don't need to be copper. This could be some sort of insulation, water, holding insulation material. So the heat doesn't transfer, at least very fast, through the thermally resistive coating. And I was thinking that potentially we would also coat these modules, but maybe not as much. I'm not sure how thick that would be.
How about if we if you seal the whole wall off from the rest of the room, then the whole wall can be at 65 and the rest of the room can be normal temperature. And then the liquid, like the air inside the cabinet, so to speak, would be 65.
Okay, that could be we've also got the challenge of, so in my other meetings, EMC emissions come up several times. And when I talk about the EMC, I'm saying these are all sealed modules. So I'm not overly concerned about EMC personally, but it has been raised a number of times. And so if we sealed off from a thermal perspective, we could also take the opportunity to seal off the wall.
Yeah, Faraday cage.
Yeah. But there was another thing as well, that this would be, and John Summers made the point, because I talked about you'd actually service this with a gantry robot. So and again, this is thinking far forward here. But so a bit like if you've ever seen the tape drive systems, like the ones from IBM, they have a gantry robot that changes the tapes. So this would be more sophisticated, but in a similar sense, a gantry robot could change these modules, either these media modules or the whole module, and potentially service the cables. And I met a company in Prague that actually does have a gantry type robot that actually manages cable plugging in a patch panel. So I began talking to them as well. So if it was serviced by a gantry robot, you could argue there wasn't a need for somebody to actually go into the room. But obviously you need super reliability for that. So the room could be held at that temperature. But so I didn't really think about the fact, he said no matter how much insulation you got, eventually that room's going to get up to the same temperature. so that was a little bit of an eye-opener for me. But yeah, so we need to think a little bit more about that, but that's a good idea, Philip. Okay, that's that. Maybe seeing we've got a bunch of thermal people on, maybe I will just open up the module itself so you can see what we've changed on the module. And one of the things with this approach, I'm thinking that we may need to make the module about maybe up to 10 millimeters wider. So go from 102 to 112 millimeters, because it's a little bit, the copper between the modules for picking up the conductive cooling is a little bit thin. It's less than a millimeter thick. So by the time you put an interconnect in there. And this is where this is my biggest concern on the thermal simulation right now, is these individual modules. They are only 25 watts, potentially 40 each. So here is the module. So if I just eject or just hide all of the modules themselves, and we just zoom in here. Come on. There we go. What you can see, what I've done is these are like electrical interconnects there. So somehow I'm assuming these would be in manufacturing, these would be made a good thermal connection with the copper plate. So this would be a complex copper plate. This is the other challenge. Can we effectively make this cost effectively? But this would be the same for every single module, no matter what. The module did, be it a switch, a CPU, a AI chip, a GPU, whatever. And you notice that I've brought the water straight into this bottom module here. So all of this infrastructure will be common. So we'd be building these in there in huge volume. So the one question is this manufacturable? But so the way this was going to be is the water would come up, the cold water would come up on both sides. It would flow down, you know, a quarter on this side and a quarter on that side. It would flow in this direction, and as it flowed as well, it would go up and down these columns. The water would go up and down to bring cold water very close to these interconnects, these friction interconnects. And these are like electrical connectors, like I said, so they're like sprung loaded here. So as you insert the module, you get a friction grip here and here, and also in here as well. So what is the thermal resistance of that interface? Could you cool that 25 watts is the big question. And maybe the likes of Samtec can help us in terms of the design of this and the material they use for their electrical connections, and we can see the thermal properties of that particular metal they use, I guess. So actually, Ender, that's an area where we're going to need to get some good thermal characterization of the materials we use here. And I was wondering if there are some other little extra pieces of material we could put in, like some maybe some gap pad underneath the springs, like in those gaps. So when it does get compressed, you get a better thermal connection with the gap pad. So I don't know. There's a few ideas where we need to modeling this interconnect is going to be a critical piece to make sure we're keeping ourselves honest on that thermal interface and the efficiency of it. So the water would have come down from the cold pipes down the first quarter here, and on the other side on the other inlet, and then they would return back up through the sensor modules, back up to the other direction. The only other thing worth noting here is that also any active cables would also have a potentially thermal cooling by the same mechanism. And this would allow us to get maybe some near packaged optics and keep them cool while being a very small module compared to the traditional optical IOs. No. Oh, so once the water's gone up the two sides and back down the middle, I've not shown it in the model here, but there would be a connection then back from this side to this top area, and we would flow across the main kilowatt processor, or up to kilowatt processor, and then it would come back up and out of the hot water outlet. So that's the flow. The only other thing we did touch on was the University of Illinois has actually did a paper on conformally coating the entire module with an insulation, and then conformally coating it with copper and getting a better thermal resistance. They claim 7 times better than a normal attached copper cooling water cooled heat sinks to the processor chips. And that may be a lower cost if it works. That may be a lower cost, and then this top lid would just need to be a water seal so that it didn't leak out of the board edge. So again, this is just very conceptual. There's a lot of analysis that needs to be done to see how viable these ideas are. So that's just a quick update of what we covered in the last meeting. Okay, next thing to talk about is anything else. Actually, before I move on, anything else on the thermal architecture discussions? Any questions or suggestions or other things to investigate?
I just wanted to give you an update, Alan. I apologize. We haven't had an engineer at Cool IT look at that model yet, but I'm gonna ping them again and just get a timeline on that. Hopefully we can get that looked at before the next meeting.
Yes, thanks, Callum. Yeah, Callum did say he was gonna take it to engineering. So thanks for that, much appreciated.
Yep.
All the inputs were all the better to see how whether this is at all viable or not. And maybe, you know, if we can get support from multiple of you on the line, then, you know, maybe we can divide and conquer in some certain areas and maybe make a bit quicker progress and simplify it for each of you. So thank you all for the input, much appreciated. So yesterday I was at Oak Ridge National Labs in Tennessee, so I just got back late last night. And I was there for, sadly, I was there for a memorial of a friend and colleague who actually worked at the lab and was trying to help us make some progress in there. So what I did with them is I actually took a data center or a HPC system downwards view of the world. I went top down. I felt that was because I in my previous discussions with the DOE, etc., I've always gone from the module up, and I think they don't get the connection of actually this could be data center worthy. So I've tried that approach. I had a discussion. There was about 7 or 8 people in the meetings, and then I had a follow-up meeting with another person in the afternoon on the system side. So it was a good discussion. They're very focused on chiplets right now, so our chiplet enablement piece of the story could be interesting, and there is this workshop coming up. I believe they're trying to target August at the moment with ODSA, the chiplet sub project. So I'm hoping that we or I can be able to be a presenter at that. But the quick summary was, I think it was a research department in Oak Ridge rather than the big machine, so I think it was more applicable. So it did catch their interest, and they are looking at doing more and more research with heterogeneous processors, and obviously they're interested in the likes of CXL and where that's going. And in fact, they showed me a couple of pictures of a couple of hairball configurations where they were actually making their own sort of modules with different heterogeneous processors and trying to patch them together in a bit of a rat's nest approach on the bench. So they quite like the idea of the benchtop version of this for them to start to experiment between different vendors of different heterogeneous accelerators and processors. So that I certainly captured the interest. In terms of the funding avenues, again, I'm not hopeful that we're anywhere near close to getting funding. I think if we can get in a channel somewhere, we may be able to actually get on a funding program. And actually, on that note, I am making a little bit more progress in Europe. I've got some things, especially in the UK, going on, where a consortium of government and companies could maybe help us get going on this as well. So I'm never giving up on the funding side of things. But just to show you what I actually, in fact, it's probably better for me to. Let me just quickly show you the model. So this was what I started with Oak Ridge, is basically I looked at their frontier supercomputer, and I'll flash the slides up in a moment as well if I can find it. So this basically would be what our wall of compute would look like. They've got effectively, Frontier has 4 GPUs and 1 CPU per node. And then they have, and the GPUs are already in OEM format. And then they have something like 9,000 nodes. So it works out they've got about 47,000 modules or HPCM equivalents. So I built the wall and compared it area-wise. So we're about 69% of the area of Frontier if they built it out of this wall of compute approach. Assuming this would work, and as well, they're 29 megawatts of power, which obviously powers the problem. You want to keep it as low as possible, but equally power density is quite an interesting factor in terms of as compute goes forward. And at 1.4 kilowatts per module, we would be able to support 70 megawatts in this compared to their 29 megawatts. So we have headroom for the, I think their GPUs are in the order of 300 watts or thereabouts each. I didn't actually do the calculation there. So so this is how I started. I started with this, and then I went down and I introduced the wall in the modules, and then we got into some discussion. We did have a little bit of a workshop discussion beforehand, where I asked them specifically. They went from the Summit machine, which was the IBM and NVIDIA machine, which was #1 in 2018 for 2 years. And then we talked about the Frontier machine, where that's been #1 since it overtook from Summit. And that's AMD CPU and GPU. And so we talked about the challenges there. So obviously usual software challenges, but there was a number of areas where things certainly run true, and this heterogeneity or the fixed architecture of the nodes was one of those not so popular pieces of it. And so in general, they do want more heterogeneity and they want more flexibility. So this modular approach did ring true. That said, obviously we are very radical, and it's obviously not deployable. We wouldn't be deployable as a supercomputer anytime soon, looking like this. But I wanted to give the vision of where this would go. So that's the angle I've been taking. But actually, one of the conclusions was, like we've said in this meeting before, was this is the vision of where this could go, but the beauty was of our approach, especially the lab, the researcher put in maybe a benchtop version of this with 4 or 8 modules supported that they can wire together in any domain-specific way they want. They were saying that researchers could make progress on applications where they want to mix AI, GPU, FPGA, CPU, whatever, and they can actually get something working on the bench in a prototype form in like the maker community, like we were talking about Raspberry Pi, and then rather than build a data center out of these modules, they could build a custom node once they got it working in a hairball on their bench, and then maybe they make a big machine once they've proven it on the bench. But the fact that this approach would allow them to experiment with specific applications. And the other point as well that came across quite well is they know they've got to be more and more domain specific. They said the energy consumption is the biggest bill, more than the actual cost of the machines, even though the machines are really expensive. And so having more separate, very specific machines that are tremendously more energy efficient because they only do that one job well is probably a trend they're going to see. And obviously with our modularity, we can quickly build very energy efficient specific machines out of this approach with the granularity we have. So it was a good meeting. But like I say, in terms of I'm hoping we might get a bit more we might get some participation out of them. The research labs, they may help us out with some bodies if we can get them interested in a research idea. So I'm keeping my fingers crossed there, but I'll stay in touch with them, and we'll see where that goes. And actually, what I'll do is I'll put the slides up that I gave to DARPA. I'll upload them at the end of the meeting, and if we've got time at the end, I might try to show it to you. Let me just, oh come on, the machine's not playing nicely to me today. In fact, I could just, while I'm here, there it is. So these were the slides. I won't dwell on. These are some slides, and these are slides I've used in the past that you may have seen, where I talk about the various composability aspects.
I think it's too big on the screen right now.
Too big. I talked about it. So I did focus that we are looking at this from an emissions perspective, as I did on the chiplet approach. This is the data center, the frontier machine in the data center, and so this was the comparison I did. Then I talked about the wall, so I zoomed in and talked about the wall, as you can see there, and the module itself. So basically that was the core presentation, and then there was a ton of other slides which were talking slides that we actually did. So I'll post those slides up on the wiki. Okay, that was Oak Ridge. Just hi, I noticed we've got a few more people attend. Hi, Suresh.
Hello.
Anyone else new? Oh, John. Hi, John. John Long. All right, I think I've got everybody. Okay, so really my final topic was, as we look forward, those of you that remember, we did a birds of a feather at supercomputing. I think it must have been 2021. Yeah, it must have been 2021 supercomputing, where we had Bob Ciotti from NASA and Trent DeHooge on the panel, and Roger Beeston and myself, and so there was one other person. So, oh, Philip, was it Philip? Can't remember. Anyway, yeah. So we had a good panel session, and I was wondering that actually it might be good to apply for the birds of a feather at supercomputing this year. And as we're getting a little bit more momentum in the different activities, we could maybe have a couple of small presentations as we make a bit more progress on the thermal side, where we can give people an update, and also on the module side as we pick a module to move forward with. So Oh, actually, by the way, I've just remembered one other call that I had in the last 2 weeks was with we were talking about CXL switch companies, and I gave you an update that unfortunately Ex-Contec are too busy with real customers to be able to help us out like they originally were hoping to do. But there is another startup called Enfabrica that have an interesting approach. They've got a CXL switch, but they've got it on CXL and over Ethernet as well, all in one switch with the CXL memory in the middle sort of thing. And so I've been talking to them as a potential module as well as the FPGA one we've been talking about. So that's a possibility. Anyway, back to the conference. So I've asked Enfabrica if they will give us an overview presentation, and hopefully one of their team will join us shortly and give us an overview so we can see what they're up to. So back to the conference. So we've got a potential of a birds of a feather at supercomputing. We've got the OCP Global Summit, and by the way, the deadline for the birds of a feather, I believe, to put your request in is the end of April. Sorry, the end of June or July. So we got a little bit of time. Sorry.
Yeah, it should be June for the deadline.
End of June for the deadline. And the Global Summit there's 2 deadlines for the Global Summit. There's this Friday for the main summit. So I might put an abstract in to give everybody, because it's 2021 since the last update I gave, and we've moved on quite a bit. Things look quite different to what we were doing in 21, at least at the on the thermal side of how we're doing things. And so I was thinking of putting a paper in then, and also Ender and Shate, you were maybe thinking of putting something in again for the Future Technology Symposium, possibly, right?
Yeah, we are planning to prepare an abstract for the Future Technologies.
So on the Future Technologies, that deadline is the end of June, so you've got a little bit more time. So if there's any interest in doing something there as well from others, then that would be that's what we're looking at. So I guess a question for everybody is would there be any interest if we actually had a birds of a feather session in being on the panel, in doing some presentations from your perspective? Like Michael, would you be able to put a Samsung angle on what you think of the OCP HPC efforts and how that plays nicely with the Samsung CXL products, and Suresh maybe likewise for Micron?
Yeah, I think let me talk about that in offline. Yeah.
Okay.
Okay.
I might, so we've got a bit of time on the supercomputing BOF, so I might try to put a little bit of a framework of what we could do in the BOF and what we could present. And if we can get from the different disciplines, we could get maybe separate presenters to give a bit more background into what we're doing and present a bigger picture. That would be good. Okay. I think that about covers that. I guess we got a little bit of time for any other business if there's anybody that wants to. Are there any topics that anybody else would like to discuss? Actually, just one question. I guess Darwish, it's been a while since you've been at the call. Is there a renewed interest from your perspective on what we're up to, or you just wanted to get an update?
A little bit of both. We have a customer chip next year, and we're in the system design phase, and so I wanted to come back in and kind of see what you guys are doing. Maybe we can adopt this new system. I know initially we talked about like the original OEM form factor, so there's some interest there as well on our side with our customers. So,
all right, yeah, that makes sense. Yeah. Okay, thanks. Okay. And Kevin, now you're with Lightelligence. Is there any chance we could have an optical module out of you? 100% optical?
That's a good question. I would say yes, but I'm not sure when.
You're a bit faint there, Kevin.
Probably the wrong microphone.
Ah, there you go, that's better. So you say yes, possibly, but I guess it's a bit futuristic at the moment.
Yep.
Okay, well, if there's nothing else, I'll give you all a few minutes back of your hour. So thanks very much, guys.
Thanks, everyone. Thanks, Alan.
Thank you, Alan.